Hello and welcome back to another episode of Math with Son. Today we're dealing still with uniform circular motion. We're doing some examples with it, and we are dealing with forces. So it kind of connects to what we were previously doing with friction and forces and all of that stuff. All right, these are pretty easy. They feel hard, but like most of them are pretty easy. So our first one, we got an object is traveling in a horizontal circular constant speed. The radius is 2.3 and the frequency is 1.1 revolutions per minute. It's a little annoying that that's in minutes. What is the object's speed? Okay, so there's a few different ways to think about this. You can think of it as what do you actually have? And if you have frequency, you probably want to deal with the frequency formula, which is frequency is equal to V over 2 pi r. And V is the speed, so we just plug everything into that. All right, well, let's do that. So V is what we're looking for. Frequency is 1.1 revolutions per minute. So if it's 1.1 revolutions per minute, how many revolutions per second would that be? Well, you just divide by 60, because if you want to turn minutes into seconds, there are 60 seconds in a minute. So you can divide by 60, and that would equal V over 2 pi times 2.3 meters. And then you just cross multiply or multiply this whole stuff by 2 pi, 2.3, and then multiply on that side. And when you do that, you would find out your velocity is equal to, I'm going to do it over here, would equal 2 pi times 2.3 times 1.1 over 60. And that would indicate your velocity is 0.26 meters per second. Okay? So I told you the math was pretty easy on it. The concept is difficult to understand, but the math is pretty easy, as I said in the last video. All right, next example. We got a 0.5 kilogram rock that is swung in the air at the end of a 3 meter long string. That's very dangerous. The period of motion is 2 seconds. What would be the force that must be affecting the string to maintain this motion? So the first thing I would do is recognize we have probably got to deal with two different formulas here, because it's asking for force, and force is equal to the mass times the velocity, the acceleration, and the acceleration would be v squared over r, and mass times v squared over r would give you your force that we're looking for. Okay? Well, we also don't have v. We do have r. And we do have m. So we could start the formula. We got force would equal 0.5 kilograms times v squared. We don't know v squared. And we don't know r. Well, we do know r. It's 3 meters. Excuse me. So we need to find v. Well, we did that in the previous example for the most part. So let's get a formula for v. V, the velocity, actually, we don't know the v. We don't know the velocity formula. We have the period formula is 2 pi r over v. Well, we could solve for v, or you could just plug in stuff and then solve for v. It's up to you. The period is 2 seconds, so if we have 2 equals 2 pi times r, which is 3, divided by v, you could multiply by v and then divide by 2, and you'd get v times 2, but then you divide by 2 would be 2 pi times 3 divided by 2. So these kind of flip locations. And the 2's cancel out, and you find out your velocity is equal to 6 pi meters per second. I don't know if you want to keep it in terms of pi or not, but I thought that the 2's canceling was nice and pretty. All right. With that in mind, we can plug in the 6 pi meters per second here. And if we do that, you find out that your force is going to be equal to, I forgot my squared. Your force would be equal to, if you just plug that in your calculator, 0.5 times 36 pi divided by 3, you end up with a force of 4.7 newtons. All right, so I'm saving you some time by understanding that. I'm hoping you can type that in your calculator to just answer. All right, we got 2 more examples. The next one I like a lot because it connects with forces. So far, it feels like we're just doing some basic plug and chug stuff. The next one deals with a car on a track. So there's a car on a track and a 9,000 Newton car, so it weighs 9,000 newtons, is traveling on a circular path with a radius of 120 meters. The coefficient of friction on the tires is 0.32. So what's actually happening here, I'll try and put it on my computer so it looks better. when you have an object like a car, there's the car, traveling, the tension, the force of tension, which is the centripetal force, is really going to be your friction. The force keeping your car from just barreling straight forward and going in a circle is the force of friction on the tires, which is why when you're going around a really tight corner at a really high speed, that means that your tires squeal and are squeaking from that force of friction being so hard, pulling you inward. Okay, without friction, you would not be pulled inward because your tires are sticking to the road. It allows you to do that circular motion. Okay, so that tells you that the force of tension, which is the force of centripetal acceleration, is the force of friction. All right, that's very important because that means that mv squared over r would be equal to the kinetic friction or static friction. I think it wouldn't matter. They give you the correlation of friction, coefficient of friction, whatever one they got, 0.32. I'm pretty sure it'd be kinetic because it is moving, but it's not moving in the way that it would typically move. Times m times g. Okay, so that is how we find the force of friction. Well, the m's are going to cancel out because we could divide by m and divide by m, so this 9,000 newtons might not even be used, because so mass won't matter. We got v squared. Do we have v squared? It wants to know the maximum speed that it can drive around the track, so we're solving for v. And we got r, which is 120, so we got 120 v squared mk, which is 0.32, times gravity. Well, with gravity, that's 10 meters per second, or you can think of 9.8. I'm going to use 9.8. That's the one I prefer to use. My answer key that I tend to look at sometimes uses 10, which always bothers me. All right, 0.32 times 9.8 is times 120 to get rid of this. V squared would equal times 120, 376.32. And then we got to square root that. And when you square root that, you get V is equal to 19.4 meters per second. Ta-da! All right, so our last example here is going to be talking about how to find the force of tension on this cord. And this cord, the force of tension on this cord is going to involve an x component and a y component, and we would need to essentially separate them and then probably do the Pythagorean theorem to find out what the hypotenuse is, because you could think of this as a right angle. And here you would have f of y probably being pulled downward, and here you would have the f of x, the force of the x direction. Okay, so how are we going to deal with that? Well, for starters, this ball, this 10 kilogram ball, is not really moving up or down, which means that the force of y is being balanced by the force of gravity. Okay, well that means that we can find out f of y pretty easily. That means that f of y will have to equal the mass, 10, it's 10 kilograms, times its acceleration, which would be 10 meters per second squared for gravity, mg. And then if we do that, we would end up with the force and direction of y would equal 100 meters per second squared times kilograms, which is equal to 100 newtons. Kilograms. All right, with that in mind, the x component is going to involve this circle, this flat circle, and the x component force would be moving inward, so it is the centripetal, I'm always having a hard time saying it, force. Okay, so what would be the centripetal force? Well, that would be equal to the mass times the velocity squared divided by the radius. All right, so let's do that. We got mass, which is 10 kilograms, times velocity. We know the velocity this time, which is 6 meters per second squared, divided by the radius, which is 3 meters. All right, we do that. We end up with a 10 times 36 ends up being 360 kilograms per meter squared, second squared, divided by 3 meters. The meters would cancel, and you'd be left with 120 kilograms per meter per second squared, which is 120 newtons. Okay. Now, both of those don't make the tension on the wire. The wire will be this part. Okay, a cord that is fixed to a ceiling. So we need to figure out this force. Well, as long as we have this force is 100 newtons and this force going inward is 120 120 newtons. As long as the units are the same, you can do the Pythagorean theorem to find the force of the tension, which would be this part. All right, so we would have 100 newtons squared plus 120 newtons squared would equal c squared, which we'll call f of t squared. So as long as we square root this, we would get the force of tension. All right, and if we do that math, you end up with 100 squared plus 120 squared, and when you square root it, you end up with 156 newtons as the force of tension on the cord. All right, that's going to do it for this one. Until next time, stay positive, my friends. The next one I'm very excited about. It deals with how does this centripetal acceleration happen when you have like things spinning. So I look forward to seeing you then. All right, bye.